Starship's biggest problem is not lifting off the pad. It is coming back. That sounds strange because the launch is the part everyone watches. The engines shake the ground. The flame cloud covers the launch tower. The rocket climbs like a steel building escaping Earth. But for SpaceX, the real test begins later, when Starship turns back toward the atmosphere and tries to survive the most violent part of the mission, re-entry. This is where the heat shield changes everything. Not because heat shields are new. Spacecraft have used heat shields for decades. Apollo had one. Orion has one. SpaceX Dragon has one. The Space Shuttle had 1,000 times. But Starship is trying to do something much harder. It is not just trying to survive re-entry once. It is trying to survive re-entry again and again, then come back, get checked, get refueled, and fly again quickly. That is the difference between a rocket and a transportation system. A normal spacecraft can burn through its heat shield, land safely, and be finished. Starship cannot work like that. SpaceX wants to become fully human. That means the heat shield cannot be treated like a disposable shield. It has to become part of a machine that can return from space many times without months of repair after every flight. This is why the heat shield is not a small detail on Starship. It is the entire business model. If the heat shield works, Starship could change launch economics. It could carry bigger Starlink satellites, larger science payloads, lunar hardware, fuel tankers, and eventually cargo for Mars. If the heat shield fails, Starship may still fly, but it cannot become the fast, reusable vehicle SpaceX is promising. The reason is simple. Starship is huge. It enters the atmosphere at extreme speed. As it falls back toward Earth, it does not just get hot from simple friction. The air in front of the vehicle is compressed violently. That compressed air becomes extremely hot, creating a plasma-like environment around the spacecraft. The windward side, the side facing the atmosphere, takes the punishment. Without protection, the stainless steel structure underneath will not survive. SpaceX's solution is a black tile system covering the belly of the ship. These tiles are designed to protect the vehicle during re-entry, while adding as little weight as possible. That is already good. But the harder part is that Starship's tiles have to survive before they even face re-entry. This is where Starship becomes different from many spacecraft. The heat shield has to survive two completely different disasters in the same flight. First, it must survive ascent. During launch, the vehicle shakes, bends, vibrates, and experiences huge acoustic pressure. The engines produce enormous force. The structure flexes. The airflow changes rapidly. If tiles loosen or fall off during ascent, Starship enters space already damaged. Then comes the second disaster, re-entry. Now the same tiles must handle intense heating, aerodynamic pressure, and changing airflow as Starship falls back through the atmosphere. A single weak area can become dangerous because hot gas can find gaps, attack exposed structure, and damage nearby tiles. So the heat shield is not just about material strength. It is about attachment, gaps, inspection, damage tolerance, and fast repair. That is why SpaceX is now testing the heat shield in a more serious way. The company is not only asking, can Starship survive? It is asking, can Starship survive in conditions good enough to fly again? Those are very different questions. A vehicle can splash down successfully and still be useless for rapid reuse. It can survive re-entry but lose too many tiles. It can reach the ocean but need weeks of repair. That would be a technical success, but an operational failure. SpaceX does not need a museum piece. It needs a spacecraft that can come back like an aircraft, at least in the long-term vision. This is why Flight 12 and Starship V3 are important. SpaceX's test plan includes modified Starlink simulator satellites that will inspect Starship's heat shield in flight. That is a major step. The vehicle is not just flying with tiles and waiting to see what happens after splashdown. SpaceX wants imagery before re-entry, while the vehicle is still in space, to understand whether the heat shield is ready for return. That changes the whole testing philosophy. Instead of only finding damage after the mission, SpaceX is trying to diagnose the vehicle during the mission. The last two simulator satellites are planned to scan Starship's heat shield and send images back to operators. Some tiles are painted white to simulate missing tiles and create clear imaging targets. This means SpaceX is testing not just the shield itself, but the future inspection Space Shuttle showed how painful tile maintenance could become. Starship is supposed to avoid that kind of slow turnaround. But avoiding it is not easy when the vehicle has around 40,000 heat shield tiles. If every flight requires a long tile-by-tile inspection, the dream of rapid reuse becomes weak. This is the brutal reality. Starship's reusability is not proven on land. It is proven when it can land and fly again without becoming a repair project. That is why the heat shield changes in economics. Rockets are expensive because most of the hardware is thrown away or heavily refurbished. Falcon 9 already changed the launch industry by reusing the first stage, but Starship is trying to reuse both stages, including the orbital vehicle. That is much harder because the upper stage comes back from orbital speed and faces the worst re-entry heating. If SpaceX solves that, launch costs could drop dramatically, not because one launch is cheaper on paper, but because the same hardware can be used repeatedly. The expensive part is not just building the rocket, it is building it, launching it, recovering it, checking it, repairing it, and doing all of that again. The heat shield sits right in the middle of that chain. A reliable heat shield means faster reuse. Faster reuse means more launches. More launches mean more Starlink satellites, more payload capacity, more NASA mission support, and more chances to build the orbital refueling system Starship needs. This connects directly to the moon. NASA's Artemis program depends on a lunar landing system, and SpaceX's Starship HLS is designed to carry astronauts from lunar orbit to the surface and back. But that lunar version of Starship depends on a larger Starship architecture. SpaceX needs tanker flights. It needs docking. It needs cryogenic propellant transfer. It needs repeated launches. None of that works well if every ship needs slow heat shield repair after coming back. Even missions that do not return from the moon still depend on a reusable Earth launch system. Tanker starships must launch from Earth. Depot systems must be built. Hardware has to get into orbit. If the heat shield slows the flight rate, it slows the entire architecture. This is why Starship's heat shield is not only a safety system, it is a schedule system. It controls how fast SpaceX can fly. It controls how quickly the company can test. It controls how many tankers can launch. It controls how fast Starlink grows. It controls how realistic NASA's lunar timelines become. And it controls whether Mars is a serious plan or just a PowerPoint dream. For Mars, the heat shield problem becomes even more important. A Mars vehicle has to survive entry into another planet's atmosphere. It has to deal with high-speed heating, uncertain conditions, dust, atmosphere density changes, and limited repair options. Earth re-entry is the training ground. If Starship cannot master repeated returns to Earth, Mars becomes much harder. The most dangerous part is that heat shield failure may not look dramatic at first. A few missing tiles can seem small on a vehicle this large, but hypersonic re-entry does not forgive small mistakes. Hot gas can enter gaps. Heating can spread. Nearby tiles can experience new loads. The structure underneath can be exposed. A tiny problem can become a vehicle-level problem because re-entry is not gentle. It is a controlled fight with physics. That is why SpaceX tests missing tile scenarios. It wants to know what happens when the shield is not perfect. This is smart because real reusable systems cannot depend on perfection every time. Tiles can crack. Tiles can loosen. Tiles can be damaged by debris, vibration, or heating. The real question is how much damage the system can tolerate before the vehicle becomes unsafe. A mature Starship cannot be fragile. It has to be inspectable, reparable, and tolerant of minor damage. That is the only way high flight rates make sense. This is also why Starship shape makes the problem harder. Capsules use blunt heat shields and usually return once. Starship returns as a giant stainless steel vehicle using a belly flop style reentry. It uses its broad side and flaps to control descent, manage energy, and position itself for landing. That gives SpaceX control, but it spreads a heat shield problem across a massive surface area. The flaps add another challenge. They are moving aerodynamic surfaces, exposed to heavy loads and heating. They help control the vehicle, but they also create difficult flow areas around the body. The edges, joints, gaps, and nearby tile regions all matter. SpaceX has understand how air moves across the vehicle during re-entry. where heating concentrates and where tiles are most likely to fail. This is why each flight gives SpaceX valuable data. Ground tests are useful, but Starship's real environment is too complex to fully simulate. The vehicle is huge. The heating is uneven. The airflow changes constantly. The structure flexes. The plasma environment is extreme. SpaceX needs real flights because real flights expose the hidden problems that computer models and test stands can miss. Every tile that survives teaches something. Every tile that fails teaches something. Every hotspot, camera view, sensor reading, and re-entry maneuver becomes part of the redesign process. That is how SpaceX develops. It does not wait for a perfect vehicle before flying. It flies, breaks things, studies the data, and changes the next version. That method is risky, loud, and sometimes ugly, but it can move fast. With Starship, the heat shield is now one of the biggest areas where that method has to prove itself. The V3 vehicle shows that SpaceX is moving from